a little more, they will allow to do computations, certain computations, many orders of magnitudes quicker than classic computers. And they represent, if they will be built, they represent a major change in our ability to compute and also a great event in physics. And it is a serious possibility that quantum computers are not possible, and this is what I expect, and I have been studying this possibility since 2005. I should say that my research agenda is very speculative, and it's not accepted by most of the experts in the community. As an example of how that I regard as speculative, I should say that in the 17 years that I worked on this topic, I didn't feel confident enough to have a graduate student working. This is something I do on myself. I have plenty. I like to have a graduate student, but they usually work on other fields, which is more to the mainstream of my interest. But now I hope I can give you some information both about quantum computers in general and also about my theory that they cannot be built, so that they represent a mirage. So in principle, failure of quantum computers is connected to the mathematical theory of non-stability and continuity, and it may have a variety of consequences in physics and chemistry. Recent claims about quantum supremacy, starting with Google 2019 announcement, are in tension with my theory, and we need carefully to study this claim, and towards the end of the lecture, I will mention some development in this direction. So here is an overview of the argument against quantum computing in just one sentence. Noisy, which I will explain throughout the lecture. Noisy intermediate scale quantum systems, NISQ systems, represent a low-level computational ability that will not allow using them for building quantum error correcting codes that are needed for quantum computation. So here I can tell you about three possible laws of physics and computation. And again, I'll get to the details later, but one famous law is called the extended Church-Turing thesis. The Church-Turing thesis tells, the extended Church-Turing thesis asserts that in principle, every computation in nature can be carried out efficiently by your laptop or by several laptops, like in more powerful classical computers. When I say efficiently, I mean that this is a technical term which is asymptotic in nature and tells that the number of operations is only polynomial in the size of the input. The quantum extended Church-Turing thesis, which is widely accepted by everybody today, asserts that every computation in nature can be carried out efficiently by a quantum computer. And the extended Church-Turing thesis will be falsified by quantum computers, because there are computations that classical computers cannot carry out efficiently, but quantum computers can. And the third law, which is implied by my theory, is not about the asymptotic behavior, but about the behavior at small scales. And it can be written as NISQ equal to BDP. NISQ is the acronym for Noisy Intermediate Scale Quantum Computers, and or Noisy Intermediate Scale Quantum Devices. And BDP is bounded depth polynomial, and it asserts that the computing power in smaller scale of noisy quantum computer is very limited. So right now, the extended Church-Turing thesis, which was a common view, implicitly at least since the 70s, is a quantum computer will falsify it. The quantum extended Church-Turing series is agreed by everybody. It is a law of physics and computation, which is not a consequence of the laws of quantum mechanics. It can be derived heuristically using various other assumptions. And we feel, and here the entire community feel, that this will be a useful addition to our understanding of the physical world. And then the third rule, the third law, NIF equal to BDP, is my suggestion, which is something that I will tell you about. But I want to begin with in the beginning and tell you the background, and I will start with computing. The basic memory component in classical computing is a bit, which can be in two states, 0 or 1. A computer or a circuit has n bits, and it can perform certain logical operations. The NOT gate, acting on a single bit, this is a gate which reverses the value of the bit, and the AND gate, acting on 2 bits, suffice for the full power of classical computing. Now, if we don't make any restriction on the length of the computation, it is well accepted that such computers with NOT and AND gates represent all the computation units. The next restriction deals with efficient computation. There are certain computational tasks that are very easy to formulate and even to check whether a suggested answer to them is correct, but which are nonetheless impossible to perform because they require too many computational steps. Efficient computation requires that the number of computational steps or gates is polynomial in the number n of inputs. So this is the notion of efficient. Now I want to mention two more. I want to mention one more very important ingredient, and this is what happens when we add probability. A single bit has two possible values, 0 and 1. But it's possible to extend the Boolean circuit model that we have bits and operate on them with gates by allowing the bit to have a value 0 with probability p and the value 1 with probability 1. In this case, the classical computer equipped with probabilistic bits can describe samples from probability space of sequences of 0 and 1. Now, adding randomness to computation was a major discovery, and it was also discovered that for classical computation, we don't really need full randomness, and we can live with pseudo-random generators that our classical computer, deterministic classical computers supply, at least for many computational tasks. And it's also a good introduction to the notion of quantum. And now I want to tell you about quantum circuits. So I described computers using the model of circuits. And now, to describe what are quantum computers, we need, first of all, to explain what are the basic computational components. And they are called qubits. And qubits is a piece of quantum memory, and the state of the qubit, rather than 0 and 1, it can be an arbitrary unit vector in a two-dimensional complex Hilbert space A. And there are two basic states for the qubit that we denote them by ket 0 and ket 1. These are these symbols. But the general state can be in superposition of these two states. And by superposition, I mean that the general state is of the form Z1 times ket 0 plus Z2 times ket 1. where Z1 and Z2 are complex numbers satisfying absolute value of Z1 squared plus the absolute value of Z2 squared is equal to 1. So qubits, a single qubit, have a sort of a continuous space of position. And they use the very important notion of superposition. And when you want to realize this by a physical system, you can realize it by, say, energy levels of the two lower energy levels of the hydrogen atom. So they can be in the lowest energy level, they can be in the second lowest energy level, and you can have superposition between these two levels. Now, after we have qubits, we need also gates, and gates are unitary transformations. We can put one or two gates representing unitary transformation acting on the corresponding two or four-dimensional Hilbert space. And like with classical computers, there is a small list of gates sufficient for the full power of quantum. And there is one additional important ingredient, which is that a qubit can be measured. When the state of the qubit is Z1 times ket 0 plus Z2 times ket 1, and this qubit is measured, we obtain a probabilistic bit with value 0 with probability absolute value Z1 squared, and value 1 with probability absolute value Z2. Now, quantum circuit, the memory of a quantum computer or quantum circuit consists of n qubits, and the state of the computer is a unit vector in a huge Hilbert space. It's the tensor power, the n-fold tensor power of a two-dimensional space. So it's a